All right, here we go. I'm going to do some limits of some more functions as x goes to infinity using M behavior models. But now these functions are going to be kind of random. So not specifically polynomials and not specifically rational functions. So we're going to have to think about what the M behavior model would be. So let's start with this guy. Limit of 2x plus sine x over 3x plus cosine x as x goes to infinity. Back in the day, the way actually my calc teacher taught me this problem, we divide everyone by x. We divide this by x, this by x, this by x, this by x. So basically multiplying the numerator and the denominator by 1 over x, or multiplying by 1, and then using limit properties. So limit of quotient, quotient limits, limit of sum of limits, and going about it that way. But we don't need to, right? So let's think about what the M behavior model would be. So when you have a fractional expression, you got to think about, well, which term is going to dominate in the numerator? So as x goes to positive infinity, which one of these terms is going to dominate? And hopefully you're saying that the 2x term is going to dominate. Now, why is that? Well, because sine x is just going to fluctuate between 1 and -1. So as you throw in larger and larger numbers in for x, sine x, it only outputs things values between -1 and 1. It's going to get no bigger than 1, right, and no smaller than -1. But 2x as x goes to infinity, this is eventually going to grow and get huge, right? So 2x would be the term that dominates in the numerator, all right? So we're going to go ahead and do that. So now in the denominator, it's very similar, right? Which one of these terms is going to dominate for large positive values of x? And the answer is the 3x, because cosine x, much like sine x, is only going to output values between -1 and 1. So we would get this. So this right here would be my EBM, my M behavior model. Now, obviously, you're seeing that I can cross these x's out. So just for note flow, I'll spruce this. The limit as x goes to infinity of just 2/3, and that's the limit of a constant. So we're going to get the constant itself. So we're going to get 2/3. So this limit would equal 2/3, right? Other information that we know, we just did a limit of a function as x went to infinity and got a number. We got 2/3. What does that mean? That means that there is a horizontal asymptote at y equals 2/3. That wasn't really the question we were looking for here, but that's just a little review. All right, so now it gets real interesting. So take a look at this guy. All right, these next two really. Not a polynomial function, right? It's an exponential and it's got a polynomial combination. It's like a sum of an exponential and a polynomial. So you can't do that. Oh, just take the term of highest degree. You actually have to think about it, right? So as x goes to infinity, which one of these terms do you think is going to dominate? And hopefully you're saying e to the x, right? Because e to a very big power is a lot more than 2 times a very big power, right? So your EBM here for this particular guy is going to be e to the x, right? And so now how would I do this, right? Because it's not like a constant. It's not a constant divided by a function. I got to think about it, right? So think temporarily for a second as x as infinity being a large positive number, right? So if I plug a large positive number in here, I get e raised to a large positive number. That's even a bigger positive number, right? So as x goes to infinity, e to the x goes to infinity. You might even remember the graph of e to the x, which kind of looks like that, right? So you're like, yeah, so why is that interesting? That wasn't too difficult. Well, because now we get to this problem, right? So this right here was your EBM as x went to positive infinity. So in other words, for large positive values of x. What is your EBM going to be here as x goes to negative infinity? Now you might think it's e to the x because it's an exponential function, x is a power, but it's actually not, all right? This is going to be the term that dominates for large negative values of x, right? This will be your EBM. Now, why is that? Well, think about it, right? If you put a very big negative number in for x, that's like, we'll say e to the negative infinity. I kind of hate writing infinity terms like that, but whatever, right? E to a really large negative number. Well, definition of negative exponents, right? This really means 1 over e to a really big positive number. So now that's constant over something growing without bound. This term here is actually going to 0. So as x goes to negative infinity, this term is going to 0. This term is 2 times a really large negative number. This is the term that's going to carry the weight. So this is the EBM here, right? So it would be 2x. And now to do this, right, plug a big negative number in for x multiplied by 2, it's big and negative. So we end up getting that. So it's kind of neat, these two questions, because you really have to think about, right, which term is going to have the most influence for either, in this case, large positive values of x, or in this case, large negative values of x. With polynomials and rational functions, we didn't really need to distinguish between the two. But with other functions, we may have to. All right, so let's take a look at this guy here. All right, so what's going on? Well, all right, here we go, right? So it's a fractional function. So which term in the numerator is going to dominate? Hopefully you're saying 2x. So, all right, I get that. So we're going to have 2x up top. And which term in the denominator is going to dominate? Hopefully you're saying absolute value of x. So we end up getting this. Okay, so now you can't just cross these x's out here, right? So you got to simplify absolute value of x. So recall that absolute value of x, right? What is it equal to? It's equal to x if x is greater than 0, and it's equal to negative x if x is less than 0, right? Remember the graph of the v? And I could put 0, x equals 0 here, or I can just say that, right? Either way is going to work, right? Again, hopefully not, this isn't driving in bananas. You're like, oh, I thought absolute value is always positive. It is, that's what this says, because if your input is negative, you have to negate your negative input to get a positive, right? So that's one way to think of it. The other way is everyone remembers that the absolute value graph looks like a V, right? It's x when x is positive, and it's negative x when x is negative. So that should not be too earth-shattering here. So now that, to me, when I come over here, I can simplify this. So I can say limit of 2x over, I'm just going to put x here. And you're like, well, why? How can you do that? Well, if x is going to positive infinity, that means x is positive. So absolute value of x is equal to x. We end up getting now able to cross these out. We end up getting limit of 2, right? So again, for note flow, I'll write limit of 2. As x goes to infinity, limit of constant self, you just get 2. All right, but notice, how would this problem have been different? How would it have been different if I went to negative infinity? Well, now when you got to this point where you're like, all right, I have to simplify that, x is going to negative infinity, that means x is negative. The input is negative here. So that means that this here would not have been x, it would have been negative x, which means my answer would have been negative 2, right? Which is kind of neat, because that means this function is going to have two r's in the last notes, one going to the right at 2 and one going to the left at negative 2, okay? The one we just showed here, though, was this guy at y equals 2. All right, so pretty neat stuff. You tend to see a lot of these e to the x expressions embedded in questions that they're going to ask you as limits go to infinity. All right, so keep an eye on that. All right, and I guess the general concept, the general takeaway from here is like, let's understand that e to a positive infinity, that's basically positive infinity, right? I cringe a little bit when I write this, but hopefully you get the idea. E to a very big number, big positive number is a very big positive number, but e to a very big negative number, right? That's just going to be 0. And you're like, why? Well, again, property of negative exponents. That really means 1 over e to a big positive number. 1 over a huge number is a small number. So these are two kind of like key components that you're going to see embedded in other problems. All right, so that's the takeaway. All right, good stuff. Talk soon.